All right, so welcome to the first video for Chapter 6. In Chapter 6, we're going to look a little bit deeper into the trig functions and how we can use them to actually solve some of these real world scenarios that we have. So that's kind of the general idea for this entire unit with a couple little things mixed in. Okay, so sometimes we call the trig functions circular functions, and that's just because of the way they relate to the unit circle. But most people try to use trig functions to solve these real world problems. You know, you probably saw that in geometry. At first, we're going to do that with right triangles, and then eventually we can do that with triangles that don't have to have right angles. So we'll see that happen. Today, we're going to learn how to solve these problems, how we can set up situations using a right triangle somewhere in the setup. I said in a couple of, well, probably in the next video, we'll extend this to ones that are not right triangles, and we're going to look at a couple of formulas, law of sines and law of cosines. So that'll be coming up in the next video. Okay, so to start off with, let's look at general rules for right triangles. So let's recall this Pythagorean theorem. So this is, you could say it as x squared plus y squared equals z squared. Some of you have probably seen it as a squared plus b squared equals d squared. But these are the sets, there are some sets of right triangles where all three sides are nice positive integers. These are called Pythagorean triples, and you probably already know some of them. So there are, when the three values have no factor, no common factor, so like, for example, 3, 4, 5, there's no number that you can divide them all by. This is called a primitive Pythagorean triple. And so this is the one that you can build other triples from. So you can generate more sets of Pythagorean triples by selecting m and n values. And you might remember this from your summer packet, are where m and m are relatively prime to one another and then getting these three values. And then we can show how the relationship will create more triples. So this is what I mean. So let's pick two values for m and n that are relatively prime to each other. Okay, so being relatively prime, like I could pick 1 and 2. Those are prime. There's no common factor between those two things. So then the two legs of your triangle are m squared minus n squared, 2mn, and then m squared plus n squared. So if I did m squared, now obviously in theory, I would have to switch that order because m, obviously the way that I wrote it here would have to be m would have to be the bigger number. So I'm actually going to go n, m. So 1 and 2, that way this comes out positive. So 2 squared is 4, minus 1 squared would give me 3. So there's one of my sides. So it's probably this one, but let's keep going. 2 times n times m. 2 times 1 times 2 is 4, and then m squared plus n squared would be 4 plus 1, 5. So there's your triple. Two legs are 3 and 4, hypotenuse is 5. Okay, let's build some more of these little triples. Okay, so it turns out that there is a Pythagorean triple whose shortest side is any of the odd numbers. So let's try to find those first. So obviously we used 1 and 2 to get us that side of 3. Let's try 2 and 3. So again, remember that first side was always the larger number squared minus the smaller squared. So that's how I got this. Let's try this. If I do 9 minus 4, I get 5. So I'm using my next two integers. If I have that 2mn, we get 2 times 1 times 2, we already said was 4. Or in this case, 2 times 2 times 3 ends up being 12. And then that hypotenuse is always m squared plus n squared. So 4 plus 9 gives me 13, or in this one, 5. So you can keep building triples with this pattern. And so really what I'm doing here is I'm just going in consecutive order and building those values. And so you can get more of them. We use these triples a lot, so they're good ones to know. 7 ends up being, if you want to pause it, you could pause it and try a few on your own. I'll fill in the chart now, so you just have those. But again, if you want to pause and try a few, you could do that. It's 7, 24, 25. For 9, we have 9 times, it would be 2 times 4 times 5, so 40, 41. 11 is 60, 61. 13, let's see, I'll just fill a couple more in. I won't do the whole chart. 13 is 2 times 6 times 7 gives me 84, 85. Are you guys noticing a pattern here? Yeah, I hope you saw this. These two, this larger leg and the hypotenuse, are always just one away from each other. And they're also prime to each other. So those are some of the patterns. Now, remember, for triples, you can also you can multiply your primitive triple and get a new triple. So for example, if I multiplied this, all of these by 2, I'd get a 6, 8, 10. That's another triple. If I multiplied them all by 3, I'd get a 9, 12, 15, which is another triple. But these aren't primitive because they're multiples of this guy. Same thing here. If I multiplied everybody by 2, I'd get 10, 24, 26. So you can keep building these nice triples. So that's kind of a nice relationship. If you want to do more, you can, but hopefully you were able to see that relationship that I was showing you there. Okay. So another concept that we should probably look at before you get started on some of these problems are regular polygons. So do you guys remember what it means to be a regular polygon? It means that all sides are congruent and all angles are congruent. So like an equilateral triangle is also a regular polygon. What would be a regular quadrilateral, a regular four-sided figure? All sides are the same, all angles are the same? Yep, it's a square. And then after that, we don't have special names other than just like a regular pentagon. So is there a way to find the measure of the interior angles at each vertex? So we're talking about these angles. Sure, if we know how much the whole shape adds up to, then we can just split it evenly. So like we know that triangles add up to 180. We know that squares angles, interior angles add up to 360. And the way that we get that sum, some of you might remember this, is you can basically just take your shape and go from one vertex and draw all the diagonals you can, and then that's how many triangles you have. So like a triangle is obviously 180. For a square or a quadrilateral, you end up with 2 triangles. So this whole shape would have 2 180s or 360, right? So if you remember this, it was number of sides minus 2 triangles. So like again, a triangle has 1 triangle, a square which has 4 sides, 4 minus 2 ends up with 2 triangles inside. If I were to do a pentagon and I drew from one vertex to and made the diagonals, again, if I connected here to here, that's not a diagonal. I have 1, 2, 3 triangles. So the number of triangles increases by 1. So that's why we can do this number of sides minus 2, because this is like 5 sides minus 2, 1, 2, 3 triangles. 4 sides minus 2, 1, 2 triangles. Okay, so that would give us how much all of those add up to together, and then you just have to divide by how many angles. And the nice thing is, like, if it's a 4-sided figure, it has 4 angles. If it's a 5-sided figure, it has 5 angles. So you just divide by the number of sides. Okay, that's going to be important because there are going to be shapes coming up in these problems where you have to know, oh, it's a regular pentagon, then that means this angle is a certain amount. So now let's look at some of them. So I did a couple pentagons and then a couple hexagons. So let's look at this pentagon. Okay, so these are regular. You can assume, I'm going to give you that. These are all regular polygons below. Okay, so the first thing we can do is get that interior angle, which is here and here. These guys are split up, so I'm not going to talk about those just yet. So for my pentagon, a pentagon would be number of triangles times 3. We've got 3 triangles, so 180 times 3. The interior sum for a pentagon is 540 then, and then there are 5 angles. So that means that each of these little interior angles is 108 degrees. So that's 108, that's 108. And technically, so is this whole thing and this whole thing and that whole thing. But again, they're split up, so I'm not going to do that. So now let's talk about how we could get the other angles in our drawing. Let's just look at this triangle by itself. Anything special about that triangle? And you can hit pause if you want to take more time to think. Well, if this is a regular polygon, that means these two sides are the same length, which means this triangle is isosceles. And that means these two little angles are equal. So I can figure out what's left. So if I use 108, I have 72 degrees left, which means each of these little angles has to be 36. Okay. And then this triangle is the same thing. So these are both 36. And then remember, this whole angle has to be how much? Yep, 108. So then I can do 108 minus 36, which makes these both 72. So this guy's isosceles as well, if you didn't already realize that. And then I can do 72 times 2 and figure out the missing little guy, and that's 36. I could have also just added these up to 108. So look, I was able to get everything in there. Okay, let's take a look at this one. This one's a little different. So in this regular pentagon, I have radii. These are actually called radii because they go from the center to the vertex of the pentagon. This is called a radius. This is an apothem if I went from here to here. So this distance, this radius, again, the reason that they call it a radius, just so you guys know if you're curious, is if I were to make, and I'll try to make my circle fairly accurate, if I were to make that perfect circle, oops, I guess I could make the pentagon bigger. That also works. If I were to line up the center of the pentagon with the center of the circle, then each vertex would perfectly hit the edge of the circle. It would be an inscribed pentagon. So when I say radius, that's because you're imagining that that center of the pentagon, which goes out to the vertexes, would be the same as if you had drawn a circle that went through each vertex. Okay, let me get rid of that little circle if I can. I have to do it like that. Okay. Okay, so then back over here. So now we know that that's a radius. Again, well, I'll do an apothem in a second. So that's a radius. And we know that it splits it into 1, 2, 3, 4, 5 congruent triangles. It has to be if you're drawing in each radius. So, well, what does that mean that I know? That means that I can actually get these little central angles if I wanted, or I could get these. That means that these two have to be the same as each other because they're next to each other and they're congruent triangles. Okay, so that's probably where I would start. So if the whole angle was 108, I would just divide 108 divided by 2, right? And so I'd get that each of these little angles is 54. And then because these are radii, if you will, those two things are equal, which means it's isosceles, so we already knew that. And then we can get this little central angle here by just taking the difference of 108 from 180. So this is 72. Now you might also remember that a central angle of a polygon is when you have two consecutive vertices connected there. That's just 360 divided by n, number of sides. You can also use that. That would get you the 72. Okay, let me add one more piece to this picture. If I go from the center to a side in this scenario, this is called an apothem. That's what we call the distance from the center to the edge. And that does create a right triangle, and it does bisect, it creates two congruent triangles. So then that whole angle, which was 72, would now get split up into 36 and 36. This is still 54. And then just a heads up, now we have a right triangle drawn, and so, you know, that's helpful with using our trig values. Okay, same idea for a hexagon, just to look at that. So again, if I was doing this, I would probably just get the central angle first. So I would do like 360. This is a hexagon, so divided by 6. So then that makes this little guy a 60-degree angle. Don't forget, it's isosceles, which means that these two have to be equal. And what you end up in a hexagon is realizing that these are both 60. So in a hexagon, it actually ends up being an equilateral triangle, just for a hexagon though. Okay. And then in this hexagon over here, again, I would probably start with this central, or this interior angle. And again, I'd have to add up all of the interior angles, which there's 4 triangles. So I would do 4 times 180. So that means that for a hexagon, it should add up to 720, but then I'm going to split it into 6 angles, which makes each one 120. So that's 120. So is that. Remember, these two are equal in length, which gives you an isosceles triangle. So that makes each of these 30. And then again, this has to be 120. So that makes this, 90. So there's a little right triangle. And then I can use a little bit of my right triangle trig to help me get these missing angles here, right? I have to do a little bit more work. What you do end up realizing is that these two triangles are congruent. This would be hypotenuse leg if you're going back to geometry, because they have this angle the same, these two sides are the same, and then they share this side. So these two angles end up being congruent. So you could actually get this without having to use trig, because this whole thing has to add up to 120. And so that it ends up that these are both 30 as well. because they have to add up with the whole thing. And then you get this little missing part, 60 degrees. So you end up with a 30, 60, 90 in there, believe it or not. Okay, so there's a lot of ways you can break down these figures, and we're going to eventually do figures that are bigger than 5 and 6 sides. So I just want to kind of give you an idea of how to break them down. Okay, so we need to talk about some parts of triangles that aren't just the sides. And so you should know these already from geometry, but let's just make sure. You should know what an altitude of a triangle is. An altitude of a triangle, it can go from any vertex and it meets that other side perpendicularly. That's the altitude, right? So a lot of people consider this the height of the triangle. And the reason they call it the height is it's because it's the distance from this side to that opposite vertex. So a lot of times it is the height. Now be careful, because sometimes you'll see an obtuse triangle and people are like, oh, I can't draw the altitude from here. Oh, yes, you can. This is the one where you have to think of this side as being the ground, if you will, and extend it. And the height is the distance still from that vertex down to that opposite side, or that height from the ground, right? So there's your altitude, there's your height. So sometimes it's outside of my circle. Okay, a median connects vertex to midpoint of the opposite side. So if I'm doing a median, then I would know that it goes from vertex and then it's going to hit that perfect midpoint. So a lot of times in geometry, you'll see it labeled so that you know it's the midpoint. That's a median. So when I say something's a median, you're going to need to know that that goes from the vertex to the midpoint of the opposite side. I think you guys are fine with angle bisector. That's not a problem. If it's an angle bisector, you know that it splits the angle into 2 equal parts. And a perpendicular bisector, of course, of a triangle would divide a side into 2 equal parts, and it's perpendicular to it. This is the only one that doesn't have to start at a vertex. Okay, so the cool thing is that 3 of these elements, a triangle has 3 of these, because I could perpendicularly bisect like each side, for example. Like I could bisect that side, I could bisect this side. What's cool is that they actually meet at one point. This point here, it's called a concurrent point when you have 3 lines meeting at the same place. And the likelihood that they do this is really low. But in these situations, it does always happen. So I just wanted to look at what that looks like, because these do have some important pieces to them. So here you go. Here's all the altitudes. So there's that altitude here, but I had to extend it. This one's altitude is outside because that's an obtuse angle. Here they are, they're meeting. This is called an orthocenter. The median, this one is very useful. If all of the medians meet, this point is called the centroid. And I love this one because it's also the center of gravity of a triangle. So usually we're in class and I like to like cut out a triangle and draw the midpoint and then balance it on my finger, and it's beautiful. I mean, it works every time. It's the perfect center of gravity. So that's a centroid, that's medians meeting. Angle bisectors meet. And they are, what happens is when you're on an angle bisector is that you're equidistant to the sides. So like if I went straight at the sides, that distance would be the same. And so a lot of you probably learned about the inscribed circle, because it was the circle, that was the center that just touched each side. And then the perpendicular bisector was the one where if you're on the perpendicular bisector, you're equidistant to each vertex. And so you can create that circle that would go through each vertex, right? So that's basically, this is the center of that circle that would hit each vertex. So we called that a circumcenter, because it was the center of a circle that went around. That's where that prefix comes from. Sorry, to go back up, this was called the incenter. And again, that was the center of the circle that would just touch each side in one place. So if you wanted to be equidistant from the sides, you would want the incenter. If you want to be equidistant from the vertices or 3 points, you would do the circumcenter. Okay. Again, you should remember these guys, how to find, cos, sine, tan, and now secant, cosecant, and cotan using the side relationships. We don't usually have our special angles in our triangles, so we do use, back in the day, they used to use a chart, but we are going to use a calculator. So let's just make sure that you guys know how to do that in a calculator. Okay, so first of all, you should know your functions for sine, cos, and tan. Now, these guys are not, this is not cosecant, guys. This is sine inverse. That's very different. So you do need to realize if you want to do cosecant, you have to do 1 over the sine button. That's cosecant. So just note to self, this is two different things. Okay, so I got my calculator here. We need to make sure that we're in degree mode for this, which is very different than graphing our trig functions because we always want it to be in radians for that. So if we're trying to solve using like the sine of something, we're going to want to be in degrees. So we just go to mode and we go down and we change that to degrees. Okay, then we can just quit that. So make sure you do that. All right, so then how do we find these values? Like what do I do if I want to take the sine of 37? I literally put in sine 37. Enter. And there I am in degrees. Okay. All right. Or there I am because I'm plugging in something that's in degrees. So this is the y value on the unit circle. If you want to do cosecant, you do not do sine inverse. You do 1 over sine of 37. That would give you the cosecant. Or of course, you could have done 1 over that answer that you got. You know, some of you have the ability to do that in your calculators. Same thing. Okay. If you want to solve for an angle where you have like, you know, cos theta equals this value, you know, 0.7453. This is when you do the cos inverse on both sides. Remember, because you're undoing cosine. That's when you do that. So this is if you're trying to solve for the actual angle itself. So like if I put in, this is when I do second cos. That's what that does. That solves for an angle. And I would put in 0.753453, and I would get about 41.8 degrees. Okay. All right. Okay. So let's try a couple of problems and see how we do. Okay. So you probably have done these in the past, and the ones that we do will be will be more difficult. They won't be as routine as this, but this will get us going. And if you want to pause after we introduce the problem and try it, you can do that and then watch with me. So, okay, lying on the ground 45 feet from the bottom of the trunk of a tall tree. So here you are. You're over here. This is you. And here's the tree. Okay. You are 45 feet from the bottom of the trunk. So that means this is 45 feet. You sight up to the top. So here you are. You sight up to the top of the tree. And the angle of elevation between the ground and the top of the tree is 71. So that angle up is 71. Obviously, I'm already drawing a model. Can we label anything? I can't help myself. I always draw it. Okay. What do we want? How tall is the tree? Here's the height of the tree, which is this opposite side. So this is what we're going to be solving for. So I'm going to call this H. If you want to stop this and solve it, go for it. If you want to do it with me, you can do it with me. So our angle that we're using is this angle of reference 71. It is a right triangle, so I can use my SOHCAHTOA stuff. So I'm going to utilize the opposite side that I want and the one that I'm given. So you're always using those two sides. So that's opposite and adjacent. And opposite and adjacent is which trig function? TOA, which is tan. So tan of my angle, make sure you're putting that degree symbol, is opposite H over adjacent 45. So all I have to do to solve this is multiply both sides by 45. So let's take a look and see what we get. I've still got my handy calculator out. Maybe. Scooch over calculator. There we go. Oh my gosh, you guys, it doesn't want to cooperate. Okay. So let's do this. So I've got 45. I can put the multiplication symbol, but it's understood as multiplication if I write it next to it like that. Okay. And so let's go to the nearest tenth. So we'll say 130.7 nearest tenth. So I'm going to say 130.7 feet about for the height. That lets my reader know I rounded it. Okay, let's try another one. Again, if you want to pause and try setting it up on your own, this would be a great time to do that. And if you wanted to work with me, you can. So we have a 95-foot tall tree that casts a 27-foot shadow. What is the angle of elevation between the ground and the top of the tree? This time I'm looking for an angle. So let's set it up. So we have a tree and we have its shadow. Okay. So a 95-foot tall tree, so that means this side of your triangle is 95 feet. And whenever we're measuring the height of something, we are measuring it perpendicular to the ground. So you can imagine that that's a right angle. And then I'm going to finish drawing the right triangle here. 27-foot shadow. So this always cracks me up. The shadow of the tree is not the hypotenuse floating around in the air. If your shadow floats in the air, you should run. That's scary. Your shadow should be along the ground. So this 27 feet, there's the shadow. And we want the angle of elevation between the ground and the top of the tree. So that would be here. So this is the theta that I'm looking for. Okay, so let's set up what we know. Well, we want this angle, and we have these two sides, which are located opposite and adjacent. So there we go. Opposite and adjacent happens to be tangent. Again, they won't always be tan. So I'm going to say the tangent of the angle I'm using, which is what's missing, is opposite over adjacent. So this is the one where to undo a trig function, you can't divide because this isn't multiplication, but you can do the tan inverse of both sides. So I'm going to take the tan inverse of this, and it should be in front, guys, because you're plugging the tan inverse in like this. These two cancel. So what I'm plugging into my calculator is tan inverse of 95 over 27, or what is the angle that gives me that ratio. So this is when I do tan inverse, so second tan of 95 over 27. And I get about 74.1 degrees. And I usually tell you what to round to, as far as, do you just want to be the closest full degree, or do I want nearest tenth? A lot of times for angles, we'll do nearest degree, but for sides, we'll do nearest tenth. But again, that could change depending on how the question is asked. Okay, so now, as long as you're setting up a model, like don't underestimate a well-drawn picture. If you can do that, you can pretty much label all of your information and start to set up a relationship, and then you can, solve any trig problem that might come up. So let's do one that's just a little bit more interesting for us. This is more our speed. Again, you are welcome to stop, pause, and try setting it up yourself. I'm going to go ahead and set it up now. So we have atop a flat roofed building, there is a 20-foot tall billboard. So I'm going to have my little building, and then here's my little billboard at the top, okay? And this little billboard is 20 feet. So from there to there is 20 feet. Okay. Standing at some distance from the building, so here you are. Woohoo! You having fun. Okay. You measure the angles of elevation from the ground to the bottom of the top of the billboard to be 42. Oh, sorry, from the ground to the bottom and then to the top of the billboard to be 42 and 46. How tall is the building? So this is what you measured. You measured the angle of elevation from you to the bottom and then from you to the top. Okay. That first one, this is a right angle always. So that smaller angle was 42, and then that larger angle was 46. And so the question is, how tall is the building? Now, the height of the building is really just this. So this is what I'm going to eventually solve for, h. Okay. So now that we have this is not as simple as before, because I don't just have one right triangle, I actually have two. So let's start with some relationships that we can set up. So let's start with one right triangle at a time. So perhaps let's start with this bottom one. So if I start with this bottom triangle, I'm going to need this length. I'm going to need this side to help me, because this side is technically in both of these triangles. Do you guys see that? That side is in this triangle, but it's also in the bigger one. So I'm going to use this side. I'm just going to call it Y. So then if I want to use this triangle, I can use H as the opposite side and Y as the adjacent. So that's a tangent relationship. So I can say that the tangent of the 42 degrees is equal to the H side over the Y side. Now I know that that doesn't help us yet, but give it a moment. Let's set up the relationship for the other triangle. In the other triangle, we have an opposite side. Careful, that opposite side is this length plus the extra stuff. So the tangent of that bigger angle is opposite H plus 20 over adjacent, which is still Y. This is where we're going to be able to do some good work, because they both contain Y. So that means I can substitute and solve. So what I would do probably here is multiply both sides by Y. And then after I multiply by Y, I'm going to divide by the tan of 42. So I have h over tan 42 equals y. You don't, there's other ways to do it, but this is just the first way I saw. And then I'm also going to solve for y over here. So then I have y equals h plus 20 on top over tan of 46. So the reason I did this is because now I know that these two things, if they're both equal to y, I can set them equal to each other, right? Because they're both equal to the same thing. So now suddenly, I'm going to scroll down, I have this relationship that will allow me to solve for the height because I eliminated the y. Okay, and this is a proportion, so I can cross multiply. So I have h times the tangent of 46 equals, so here I have h plus 20 times the tan of 42. I'm going to have to distribute that because I need to get the h's together, and there's no way for me to do that without doing that. So I'm going to go ahead and distribute that. Okay, and then the only way for me to solve for h is to get any term that has an h on the same side. So I'm going to go ahead and subtract this guy and move it over there. So I would have h times the tan of 46 minus h times the tan of 42, and that would be 20 tan 42, which this is just a number. So now what can I do to get h alone? I can factor it out. That's why I needed to bring the h terms to one side. Notice I have not plugged one thing into my calculator because I am keeping it nice and exact. Last step would be, this is multiplication, so we're going to divide. So I have 20 tan 42 on top over tan 46 minus tan 42. Whew! Okay, let's plug that baby in. Now, frankly, there is a way to put in fractions to your graphing calculator without using the division symbol. If you go to, I think it's alpha y equals, yeah, there we go. One more time, I'll show it again. Alpha y equals, and it's that first button, fraction. This says created numerator, denominator. Just hit enter and it puts in the fraction. It just keeps you from having to use so many parentheses. So then I'm just going to type in my top, make sure we close off that parentheses, type in my bottom, making sure I close off my parentheses because you'll get very different answers. Okay, make sure you've got that in there correct and hit enter. So we end up with the height of the billboard, H, as being 133.2 feet. Okay, this is more realistic as to some of the harder problems that we're going to start doing, and I'm sure you guys are going to have some questions as we go along because there are some tricky ones, right? So be prepared for that. And then the last little thing I just wanted to point out is, again, making sure you know the difference between angle of elevation, which is from the ground up, and then we also have something called angle of depression, which measures from the horizon line down. So just to give you a quick example of angle of depression. So if you had a hiker who was standing like on the edge of a cliff, right? So here you are, woo. Whenever you're above and you look down, so like being on the edge of a cliff, being in an airplane, you might look down at something, or hot air balloon, you're looking down. So I could tell you that, maybe you're at the top of like a 200-foot cliff and you use an angle of depression to maybe sight like a campfire, down here that's going, and you're excited about it and you want to go to it. And so you're getting yourself, you're trying to figure out how far away it is. And I'm trying to use orange and it just does not want to use orange. I was all excited about drawing a little campfire for you guys. There we go. Okay. So when you spot this campfire, you look out and then you depress to look at it. So the angle of depression is out here, not here. It's from you looking out and depressing down. So maybe you spy it at an angle of like 54 degrees. And you want to know how far. You can do two things. You could either figure out how far you are from the campfire, like if you were somehow able to zip line, or if you walked down to the bottom of the cliff, how far you'd have to walk on the ground to get there. Again, this distance would create a right angle. You have a little right angle there. Okay, so if I was trying to solve for this, I could find this angle because these two add up to 90, or these two angles form a pair you learned in geometry because this line, the horizon, and the ground are always parallel. Do you guys remember? They form a Z pattern. These are the alternate interior angles. So that depression angle actually ends up being the same as this angle up here. Or I'm sorry, down here. So then I could solve. Again, this one happens to be tangent, because if I want this distance, for example, I'd use opposite and adjacent. Or if I did want the distance between you and the campfire, if you could zip line down there, which sounds kind of scary to the fire, but if I did that one, then I would have opposite and hypotenuse, which would be sine. So I'd set up sine of 54 equals 200 over y. Don't freak out if your variable's on the bottom. All that means is you need to multiply both sides by the denominator first and then divide by sine of 54. Okay. Okay, so you'll be ready to try 20 of my nearest and dearest now. The first half of that 20 of my nearest and dearest are all right triangles, and they're pretty easy stuff. And then the second half, we will get into some a little bit crazier uses. You can use law of sines and law of cosines, which is in the next video. Okay, good luck with this.